Standard generative AI is reactive. It waits for a human prompt. Agentic systems are proactive, designed to perceive their environment, decide on an action, and execute cascading, multi-step workflows. Enterprise IT infrastructure was built over decades with a core assumption. There is a physical human sitting at a keyboard, manually authenticating every request. Agentic AI breaks that assumption. We now have non-deterministic algorithms making independent decisions, yet we are handing them the administrative permissions to interact with secure databases, APIs, and production tools. This introduces specific attack vectors, like credential replay. If an agent's access token is passed into a large language model's context window, an external attacker can use prompt injection, tricking the model into surrendering those credentials to gain unauthorized access to the network. You cannot safely scale agentic workflows until you can mathematically guarantee both the identity of the agent and the intent of its actions. Securing this system starts by mapping the path of execution. A standard workflow begins with a human user authenticating through an identity provider, moving to a chat interface, routing through an orchestrator, down to specific agents, across a server protocol, and finally hitting a tool. Every agent in this flow must be treated as a non-human identity. Before an agent can connect to any system, it must prove who it is to the central identity provider. This prevents a rogue, unverified algorithm from spoofing the system and stealing data. But knowing the agent's identity isn't enough. We must ensure the agent is not acting unilaterally, but rather through delegation. The system needs cryptographic proof that the agent is operating explicitly on behalf of a specific, authenticated user. The identity provider accomplishes this by fusing the human subject and the AI actor into a single, verifiable credential. Without this combined delegation, an autonomous agent is an untraceable insider threat. With it, every action the AI takes maintains a direct, unbroken chain of accountability back to a human. This chain of accountability has to be verified at every step. Whenever an agent passes a task to another agent, or to a Model Context Protocol, or MCP, server, the system performs a dynamic token exchange. During this exchange, the system applies the principle of least privilege. The incoming token is swapped for a new one that is stripped down, containing only the absolute minimum permissions required to complete that specific operational hop. The final, most sensitive step is the last mile. The moment the MCP server must physically interface with an external enterprise database or tool to execute the task. If the server holds permanent credentials to those tools, the entire system is at risk. Instead, a secure vault provides a temporary, just-in-time credential to the MCP server that expires the moment the task is complete. This node-by-node token exchange ensures that even if an agent is compromised, its access is locked into a highly restricted scope. It cannot escalate its own privileges across the broader enterprise network. This diagram illustrates Anven Treecapital's sovereign intelligence solution. It executes trust workflows entirely within isolated environments. By deploying in air-gapped virtual private clouds, no data leaves the firewall. Communications are secured with mutual TLS, and data at rest via envelope encryption. To address the risk of the model hallucinating incorrect actions, Anven grounds all of its agentic reasoning in verified internal data. Using retrieval augmented generation, the AI can only pull from established corporate knowledge before it formulates a plan. Looking at this framework, Anven enforces role-based access control natively. The infrastructure restricts access directly at the identity level, guaranteeing an AI agent can only process and view information its human user is explicitly authorized to see. True AI security in the enterprise requires moving beyond renting public APIs and sending proprietary data over the open internet. It requires owning the entire underlying cognitive infrastructure. Even with perfect cryptographic security, autonomous execution carries operational risk. This is why any high-stakes agentic deployment requires a human-in-the-loop control plane. Before executing a critical task, the agent generates a reasoning chain and execution plan, then automatically causes. At this checkpoint, a human reviews the AI's logic for missing context or compliance risks, granting final approval only when the plan is flawless. This intervention acts as a continuous feedback loop. It corrects the agent's underlying behavioral logic, so the same mistake isn't repeated. A zero-trust architecture empowers the AI to execute, while making it structurally incapable of acting outside the bounds of human intent.